functions. Let's have a look at this, because I think it moves on quite nicely from what we've just been looking at, this idea of using logarithms to solve indifferential equations. We're going to use logarithms now to explore this function. And that's a very common type of function. We have some data. In this particular experiment, we've measured the current flowing and the power dissipated in a circuit. So it'll be some sort of voltage across a resistor, and we're measuring the power loss across the resistor and the current through the resistor. Prove that the law relating current and power is of this form. So often in engineering we find this sort of relationship coming up. Y, in this case the power, is related to X, which in this case is the current, multiplied by some constant and raised to a power. And what we have to do is find out what this power is, n, and what the value of r is, the constant in here. So we go about it by using logarithms to rearrange this formula. Power equals Ri to the n. We've got a power in there, n, and we want to find out what n is. And so we use logarithms, because if I take the logarithm of both sides, I can bring that power down and turn it into multiply. So take logarithm of both sides. Logarithm of power equals the logarithm of Ri to the n. Using laws of logarithms, I can say the logarithm of p equals the logarithm of r plus the logarithm of I to the n, because of the laws of logarithms. Multiplication becomes addition. As before though, and with these industrial equations we've just been looking at, because I've turned this log I into a power, I can then bring the n down and that becomes a multiply. So finally we've got that log p equals log of r plus n times the log of I. This looks like the equation of a line. Y equals mx plus c. So I want to talk a little bit about the equation of the line, remind you of that, because it's something that you will have done before. So we'll just revise that, and then we'll see how it relates to this. So if I plot two variables, y against x, in this case it's power against current, or log power against log current rather, for any two variables. If I plot y against x and I get a straight line, then that means I can write down the equation of the line. And I'm hoping you've seen this before that relates y and x. Could anybody tell me what C represents? Yeah. Good. Yeah, where it goes through the y-axis at x equals 0. That's the word you're looking for, yeah. The y-intercept. So C is the y-intercept, where it cuts the y-axis. Here, in other words. Okay? So that's what C is in this equation of the line. M is the gradient. So I draw a triangle on this line, and the convenient point is often where it cuts the y-axis. So I draw a triangle in, and I work out what y is and x is. So I measure y using the scale from here, from there to there gives me y, and from there to there gives me x, and divide y by x to get the gradient. And that is the value of m in this equation. So that's the equation of the line. help here, if I rewrite this we had at the end of this side, we had log p equals log r plus n log I. If I write the n log I first, so log p equals n log I plus log r, which is what we had before, but I've just switched the two terms on the right hand side. And now underneath, if I write the equation of the line, we can see a direct relationship between the two. Checking. So what we're saying then is, and these are the important points to come out of this, I've rearranged this function. Remember we had power equals Ri to the n. So we could write that here actually. Power equals Ri to the n. Using laws of logarithms, we've shown that that can be written like that. So this is another way of writing that. If we write this formula here, or this function rather, like this, then if we can compare it with the equation of the line, we see that actually instead of plotting power, if we were to plot log of power, and instead of plotting I, we plot log of I on the x-axis, then if we get a straight line, that means that we were right when we said that the relationship was power equals Ri to the n. So the question says, prove that. And so by getting a straight line, when we plot log power against log of the current, we've proved that it is of this relationship, because otherwise we wouldn't have got a straight line. Once we've proved that it is a straight line by plotting log power against log current, then the gradient of that line will give me the value of n in this function here, and the y-intercept will give me log of r, which means I can then find out what r is in this. So what we do is, and we're going to do this after the break, is to find out what log of each of the p's are and log of each of the currents is, plot log power against log current on a piece of graph paper. Hopefully we'll get a straight line. If we do get a straight line, we're going to find the equation of that line and find the gradient of the y-intercept, which will then give us these values here. Okay?